Hi, we're starting a new unit, Unit 13, Ethers and Epoxides, and I want to start by going over some simple naming and discussing a couple of important properties. Now, an ether is a molecule that has a carbon, oxygen, carbon functional group. Typically, the carbons flanking the oxygen are going to be sp3 hybridized. You know that oxygen here has two lone pairs. One of the more, or maybe most useful ethers is diethyl ether. And diethyl ether looks like this. Diethyl ether is a common name. Basically, for the common name, you're listing the two alkyl groups on the sides of the oxygen. So since we have two ethyl groups, we'll call this diethyl space ether. The IUPAC name, how to name this systematically, you want to consider one of the sides as the substituent and the other side as the parent. But it's symmetrical, so it doesn't matter which one you think as the substituent. But if this is the substituent, then the parent chain would be this 2-carbon chain and ethane. So you just treat this as any old substituent like bromoethane or methanol. Oh, did it say methane? Ethane. 1-bromoethane or ethanol. But here we have what's called an ethoxy group. So that's ethoxy. It's the oxygen with an ethyl group. The IUPAC name for this is ethoxy, no space, ethane. Now, if this group was on carbon number 2, then actually that carbon would be carbon number 1. That's why you don't put a 1 here. You don't say ethoxy 1-ethane. Let me go over one other example. Or maybe, one other example for now. Let's try this one here. Alright, this one's interesting because it's not symmetrical. If I was to name this using the common nomenclature, we have two groups. We have a tert-butyl and a methyl. When you have tert-butyl, you alphabetize based on the B. This would be tert-butyl space methyl space ether. But what about doing this systematically? Well, the side that has more carbons will be the parent, and then this side will be the substituent. For ethers, I typically circle the substituent first, and then you could just treat this like a substituent. Pretend this is bromine. How would you name this molecule? Well, you would number it like that. And then we have another substituent, a methyl group. You want to alphabetize your substituents. We have a 2-methoxy versus a 2-methyl. I think this is 2-methoxy, 2-methyl, no space, propane. I might have misspoke. I think common error for this one would be 1-ethoxyethane to locate where the ethoxy group is. But again, we don't put a 1 here because if the ethoxy group was on this carbon, that carbon would automatically be number 1. But here it doesn't matter to list where the methoxy group is or where the methyl group is. Okay, now we'll do more nomenclature a little bit later. In terms of properties, diethyl ether, right here, diethyl ether was used as an anesthetic in Boston for dental surgery in the 1840s. 1840, a dentist in Boston use it as an anesthetic. The issue with this is that ethers are typically very, very flammable. And over the years, scientists have been making derivatives of ethers to still act as anesthetics, but reduce its flammability. And one of the more popular ones developed was isoflurane. Let me give you the condensed structure. What's going on here is that when you add halogens, that's a chlorine, when you add halogens to an ether, it reduces its flammability. Yeah, so this is very halogenated. It has fluorines and chlorine. So my question to you all is, can you draw the line structure for this? Can you figure out what's attached to what? I won't give the answer right now. If we have time, we'll come back to this. Draw the line structure. Okay. Let's do one more. Actually, I do want to list this. You add halogens. Okay. One more naming. At least for the simple ethers. Let's try this. Okay. Which side will be the parent? Which side will be the substituent? It looks like the side on the left has less carbons, so we'll make this ethoxy group or alkoxy group a substituent. And we also have a bromine here. When you number your parent chain, start from the end closest to a substituent if it's an alkane. I think that is the correct numbering. Alright, the IUPAC name for this, bromo comes first. 1, bromo, 4. You have 3 carbons. Propyl. You have an oxygen, so this is propoxy. Just like methoxy, ethoxy, propoxy, hexane. No space. Just double check. We alphabetize based on the B and the P. Over here, just as a reminder, we alphabetize based on the B and the M for this common name. Okay. What other ethers do we have? If we have a cyclic molecule, okay, there's a very simple cyclopropane, and we have a alkoxy group attached to it. Let's make it like that. When you have a ring, the ring is going to be the parent no matter how large the alkoxy group is. This is the parent, cyclopropane, and the substituent is this one, because the ring is going to be the parent. One, two, three, four, five. Pentoxy. Cyclopropane. Remember, when a ring has one substituent, you don't locate where that substituent is, it's always on carbon number 1. Alright. Now there's one very useful cyclic ether, and that's the one with a 3-membered ring. But when I say cyclic ether, the ether part is within the ring. Let me show you what that looks like. Cyclic ether. The example I'm thinking about is this one right here. The 3-membered ring. The ether functional group is part of the ring, not a substituent. This is called a oxirane. There are a couple of acceptable IUPAC names. This specifically is oxirane. Okay. But in general, people know this as an epoxide. Or it's a class of molecule called epoxides. I'm not going to tell right now how to name more complicated epoxides, but you know, even if it has groups, such as maybe something like this, isopropyl and methyl, this is still an epoxide. It's a class of molecules, an epoxide. It's actually pretty reactive because it has a lot of angle strain, but that, you know, reactive molecules, those are important in organic chemistry synthesis. Okay, let me go over a couple of important properties. We already saw one, it's an anesthetic, but it's also flammable. You know, ethers, they are polar aprotic solvents, right? Let me give us another ether, one that is often used in the lab. I'm going to use the common name for this one. That's what's called a vinyl group. So that's a vinyl group. That's a ethyl group. This is called ethyl vinyl ether. Again, this is a common name. Alright. Ethers are, when they're liquid, they're polar aprotic solvents. So they do accelerate, right? Accelerate SN2 reactions. Or maybe not reactions, but mechanisms or pathways. One common solvent is this one here, a cyclic ether again. This is called THF. One last interesting solvent. This has multiple ether functional groups. The common name is called Dikeline. And it is a high boiling point. You know, if you have to push the reaction by heating it very, very high, it's not useful to use water because it has a boiling point of 100. Dikeline has a boiling point, I think, over 200, so it doesn't evaporate. A high boiling point, again, polar aprotic solvent. Okay. Now, ethers, in terms of another useful property, ethers are less dense than water, and they are not miscible. So, let's say we have water, and the ether layer floats on top. Oh, I never said this, but diethyl ether, again, is a very popular solvent in labs. It's abbreviated as ET2O, 2 ethyl groups, oxygen. So this is good for extraction. It's less dense than water. But it can typically dissolve organic compounds if you want to separate it from the rest of the mixture. Okay. Is there anything else I want to say about this? So again, it's immiscible in water. That may or may not be a surprise to some people. It can do hydrogen bonding, right? But again, these ethers, the hydrogen is not covalently bond to the oxygen. So these are hydrogen bond acceptors. For instance, if I have this ether right here, okay, we all know that this oxygen is partial negative, rendering the neighboring carbons partial positive. But if you wanted to participate in hydrogen bonding, we need a hydrogen bond donor. Let me use ethanol like this. Okay. We have partial negative here, partial positive here. This is a hydrogen bond. And being a little more specific, this is a hydrogen bond donor because the hydrogen is on this molecule, and this is the hydrogen bond acceptor. Okay. We also have dipole-dipole interactions, right? This is not a hydrogen bond. This is dipole-dipole. Still, diethyl ether will be immiscible in water. Okay. I'm not going to do it in this video, but there are 3 ways to make ethers. First way is to link 2 alcohols, 2 of the same alcohols. So for instance, we'll call this A. There was a substitution, and that substitution, because it's primary, would be SN2. In the next video, I'll go over the mechanism for this. The next one is the one that's really, really popular. It's called Williston ether synthesis. And that's where you take an alkoxide, and it doesn't have to be primary, so let me make this actually secondary, and you react it with an alkyl halide. Another SN2. Letter C is a method that most professors teach, some don't. That is this technique here. You use an alkene. For some of you, this may look familiar. This is oxymercuration. When you have water, you add an OH, but when you have an alcohol, you add an alkoxy group. Let me draw you that product here. On the more substituted carbon in the double bond. Okay. Oxy. Actually, because we're adding an alkoxy group, this is alkoxy. Oxymercuration for the mercury, and then we remove the mercury. So this is the second part is demercuration. Some of you all may not have been taught this. It is in the textbook. It just depends on the semester whether we include this on the exam or not. And maybe I never wrote this down, but you know, all of these are alkoxy groups. Let's see. See, this ethoxy, this is an alkoxy group. Methoxy, ethoxy, propoxy, propoxy. Alright. In the next video, most likely I can fit the mechanism for these 2 reactions, A and B.